Welcome to video 3. What we're looking at here is the human brain. Now the reason I want to just go off topic very quickly is it seems our thought processes are a very strange, very odd thing. Thinking about things sometimes is it's very cloudy. Sometimes we get very confused, sometimes we don't really quite understand things properly, sometimes things just seem very difficult. Then all of a sudden one day things click into place, and sometimes things that seemed very difficult in the past are all of a sudden very clear and then very precise, and they seem so simple once we understand them. And simple things often viewed sometimes as the most complex, and sometimes it's the opposite way around as well. Sometimes complex things turn out to be simple, sometimes simple things turn out to be complex. So I just want to show a couple of pictures of the human brain so that we can think to ourselves that sometimes what we think about is not always as complicated or always as difficult as what we may think initially, and there is a certain amount of thinking that is required to step past the point of complexity. Sometimes we have to sort of think to ourselves, well, we need to break this down to the smallest pieces to actually make it simple. Okay, and the human brain looks all complex. There's lots of wiring and lots of different bits and all that sort of thing, you know, brainstem, nervous system, and all that sort of things all connected. It all seems so complex, but if we stop and if we think to ourselves, right, we need to make this simple, we need to break it down to the smallest possible pieces, and before you know it, everything seems much more simple, much more elegant, and obviously things start to make sense and things can be put together in a simple way that makes for cheap, simple experiments that make sense and work. So that's what this part is about. I encourage everybody, I'm going to leave the comments on this video open, encourage everybody to step in and give us your opinions and all that sort of thing. I'll do the best I can to read through. I'm not going to reply to troublemakers, so if it's a sensible comment, if I think it's a sensible comment, I will try the best I can to reply, but I'm not going to waste time dealing with people that are trying to waste our time. Okay, so please make a comment, tell me what you think. If you disagree with what I've sort of just said, please give me your opinion, because that counts to me. That really is important. Alright, so what we're looking at here, I always start with that, I don't know why. Anyway, what we're looking at here is what we are familiar with already. Okay, we've got 3 coils. Okay, Nikola Tesla's favorite number, or one of the favorite numbers, was 3. 3 is asymmetrical any day of the week and every day of the week. Obviously 2 is symmetrical, but that's not what we're aiming for, and that's the point I'm trying to get across. The point I'm trying to get across to everybody is we're looking for an asymmetrical system, a system that doesn't obey the symmetrical laws of electromagnetism, okay? Because electromagnetism, when it's symmetrical, you're looking at a energy transfer from, for example, a primary coil to a secondary coil, which would be equal and opposite, less losses. Okay, and that's the critical thing. Equal and opposite, less losses. So a symmetrical system can never ever ever go above unity. Okay, and that's why I've chosen the Above Unity website, okay, aboveunity.com. So a symmetrical system can never go above unity. An asymmetrical system can, however. Not always going to, but it can. Okay, and when I say can, it means we need to use our brains like we've just gone through. We need to think logically, we need to break it down, we need to make sure that the simple rules of electromagnetism are followed, And again, it is all simple. Once you break it down, once you sort of obey the rules of a changing current will induce a voltage. Okay, those simple rules, if we sort of follow those simple rules, then it will make sense. We will get to the point where the light down here, even though we have a non-inductive coil here, okay, or at least what is thought of as a non-inductive coil, we will get the light to light for a very, very minimal input on the power source over there. Okay, so our power source really is only to bring the voltage up on the terminals. Once we have a voltage, we can then effectively draw the current. The current is a force that is equally balanced between L2 and L3. Okay, and this is the asymmetrical part of the system. You can see here I've got my previous primary coil that was up here, that's gone now. The same coil arrangement over here, but now I've got a coil here which is 12 turns, and that's going to be my new input coil. Okay, this is what's called a unity coupled. When a primary is wound over, or I should say it the other way around, I should get it right. When a secondary is wound over a primary, it's called unity coupled. But unity coupling basically means, the definition basically means that one coil is wound over top of the other one directly and is not on a different part of the coil like it was before. Okay, so that's, as far as I'm aware, that's unity coupling. Okay, we have our same measurement block over here. The measurement block's pretty important. This has helped me a great deal in understanding what the currents are doing and where they're going. I think that's fairly important. I was running a little bit blind in the early days in some of my early experiments, only really going by feel, so I was sort of at the stage where I had to have enough current flowing in the coils that I sort of really needed to know what was going on, so that I could either hear, see or feel that there was a difference in current. Okay, and that was sort of a little bit blind. I was running a little bit blind, which I recommend. It doesn't cost much, it's very, very easy. These sorts of things can be put together for minimal cost. I mean, the resistors themselves, I recommend a 0.1 ohms up to about 5 watts. I'm pretty sure these are up to 5 watts. It's a 1%, so 1% of 0.1 ohms is pretty small. So 1%, 0.1 ohms, metal strip through hole resistor. They're fantastic. They're worth their weight in gold for a couple of dollars. I think it was about $3.50 I think I paid each one, which was a little bit more on the expensive side considering I only bought like about 5 of them or something like that. When you buy 10, the price drops down even further. So the coils are the same as what I have shown all along. My famous gold coils with the green input coil. Green input coil indicating fewer turns on the input as what we require on the output coils. And there's a very good reason for that. Hopefully very soon we will show you that. The more turns the better. You've got to remember these effects come from a changing magnetic field. Okay, a changing magnetic field is considered to be a MMF, magnemotive force. Okay, and it is the magnemotive force which is what starts to get charge built up, so that would create a voltage on one end of the coil. Okay, and then that charge built up on one end of the coil would then create a current to flow through the whole coil. Okay, the electric field obviously between the two would then create a charge that would flow as a current. Okay, current again very important. Okay, I just want to say most of my previous coils, I've said it before, most of my previous coils you'll see there'll be a lot more turns than what I'm showing here. The reason for that is the turns and the current and I've always said get your current up so you can see what you're doing. Machines with a couple of micro amps of current, it's going to be almost impossible to see what's going on. You'd have to use the scope, and then there'd be a very fine line. You have to make sure your measurement probes are all right, all that sort of thing. It'd be much harder. Now, even then, with microamps, or even with say 10 milliamps, is really not enough. You need to get, in the order of several hundred milliamps. Anything less than that's going to be very hard to do what we're talking about. Okay, so the amps through the turns, Ni, which is ampere turns, that's the old measurement. I forget off the top of my head what the new measurement is, but the ampere turns is what does the work for us. And you've got to remember, because we've got two output coils, it is the ampere turns between the two coils. So this coil over here has ampere turns of, say, 50. Okay, this coil over here, say, ampere turns of, say, 50 as well. So the ampere turns will be different between this coil and this coil. This coil will see the change of ampere turns in this coil over here, and this coil here will also see the change in ampere turns in this coil over here. So it's the difference. Remembering the key function of a generator, the reason we have to spin the shaft is for the change in magnetic field. Okay, so the reason we have to spin the shaft, the reason we have to put torque onto the shaft, is to get a change in magnetic field. Okay, now like I've said before, the current, if we let the current go on one of the coils, so if we instantly disconnect this coil over here from the system, then the magnetic field in this coil over here would instantly fall to zero. Okay, there'd be a exponential decay to zero. But if the ampere turns and the current in this coil is slowly decaying over time, and you've got to remember, because they oppose, okay, so if we were to do a big spike, all right, the big spike, so we've got, between the two coils, we've got 10 volts, okay, so we've got a 10 volt spike, which, yeah, okay, it's a little bit, you know what I mean. So we've got a 10 volt spike. We instantly get these coils connected in at that 10 volts, okay, there's going to be a slow decay over time, okay, and because they oppose, one's going to fight the other, okay, which you've got to remember, the generator, there's a fight on the shaft, okay, there's torque trying to turn it one way, while there's a negative torque trying to turn it the other way. So that fight occurs between our partnered output coils. Alright, it doesn't occur between our input coil and our partnered output coils. Okay, if it does, then we've got something wrong in the system. We should see a reflection back on the primary coil, which should actually reduce or assist in its operation, which is opposite compared to what we currently have in a symmetrical system. Remembering, symmetrical and asymmetrical, totally different things. Symmetrical, we've got two coils, okay, remember, between two coils it's a transfer of magnetic energy, which is the ampere turns, voltage, current through turns N, which is a transfer of energy, electrical energy, between the two coils, which is equal and opposite, less losses. Okay, so a symmetrical system always is a below unity system. An asymmetrical system can go above unity. Okay, an asymmetrical system, once it's tuned right, once it's brought into its correct running function, okay, it then will move into above unity, because the magnetic fight occurs between the two partnered output coils. Okay, so our input coil is just to get these guys excited, just to get them in the game, just to get them playing ball, and then these guys can be the two footy teams and then do what they need to do. Fight's all on, who's going to win? Alright, so I'm going to move on a little bit. We're going to plug it all in. Just going to show you our input coil turns. Again, 12 turns coming out the back, not yet connected. We're going to stop the video just for a minute. We're going to plug it in. Now you'll see on my H bridge, I've already taken off the H bridge. I now have 4 single channels. Okay, MOSFETs that switch via the circuit. Again, you'll see all this on the website. Okay, all this is on the website. Reliable and flexible switching system. You'll see how I've built that. You'll see other systems that I've built, all that sort of thing as well. So look it up. We on our aboveunity.com, we've gone into all sorts of things. We've gone into electronics. We've gone into microcontrollers. We've gone into all sorts of things. I'm a C# programmer. I've done other programming languages as well, C++, C, a little bit of Java, a little bit of Python, not very much, but a little bit. I quite enjoy programming, but it's a bit tedious with some languages. Some languages are just really painful. Anyway, so again, we've taken this is our power cord, plugged into our PSU. We're going to start off with a really low voltage. Okay, we've got 12 turns, so we're going to start off with the lowest voltage that our PSU can supply, which I think off the top of my head is about 2.7 volts. So we're going to have that 2.7 volts coming through our measurement block up to our capacitor bank. You've got to remember we've got diodes there, that protection diodes, so there is a voltage drop across these diodes, which is a bit of a pain to be honest, but you've got to remember that there's a loss in the system, including not just the diodes but the capacitors, the resistance, okay, over here, the wire resistance. So there's losses in the energy that we're transferring before we even get it into the system. You've got to remember that. So so output over here, we're going to have 1 to our coils, 1 to our negative, and obviously the other coil to over here. Alright, so I'll go through, we'll set all that up. Again, we're going to start off with a very low duty cycle. We're going to find a frequency that the system likes, that brings the system into resonance. Again, I just want to repeat, because some people don't go back and look at the old videos. I wish they would, but they sometimes don't. This coil over here and this coil over here, I term them as partnered output coils. They're 2 output coils, 2 separate output coils. Both have a function, okay, but they must be in resonance. We must find a resonance, because at resonance, that's when we get our standing wave. Okay, now everybody knows that resonance systems, when they are resonant, they either have the maximum impedance or minimum impedance, depending on the system, depending on how you have the system set up. In a standing wave, when we have a standing wave, we want to find the minimum impedance where these coils effectively have no impedance, okay, no reflection if you like, no negative effects to the system. Okay, so it's going to be a very, very low impedance to zero impedance system, which would show up as no load, or at least even a negative load, on our primary coil. Okay, remembering that this is magnetic resonance, so the coils must have currents that are 180 degrees out of phase, and we must find maximum amplitude on those currents between the 2 coils. Okay, so turn for turn, for each turn that is folded back on itself, because remembering this part up here, this entire coil, for the layer underneath, the entire coil, if we have currents out of phase, so in other words what I'm saying is one current moving up on this wire over here and the other current moving down on that wire over there, so for each current up, the current back makes that piece, that turn, that piece of wire
it makes it non-inductive. Okay, so in other words, what I'm trying to say is a changing magnetic field over here would not induce any voltage on this part of the coil over here, because this part of the coil over here is non-inductive. Okay, non-inductive. Basically, it has to be inductive for there to be any magnetic transfer of energy between the two coils. So the only part of the coils from this primary coil that is inductive is this underneath part up to that point there. Okay, so again, I've gone through this before in the other videos, so those following will already know, but turn for turn there is 3.7 times inductive coupling, or at least a inductance factor between this coil and this half of the coil. So we're 12 turns compared to 45 turns. Alright, so it should be a step up factor, and we should see a voltage difference on the input of 3.75 times more between this part, this coil over here. Okay, you can do the math yourself. 12 into 45 and you'll see the figures. Alright, okay, so we're gonna get this all together again. Output, that'll be the output over there. Again, anything up and back is non-inductive. Okay, so we've got to remember that. Okay, I'll pause the video and we'll carry on. Alright, so we're back, guys. What we've got is everything connected. We've got a little bit of a light, we've got a little bit of light on it. We've got a very small 0.22 microfarad capacitor directly across this coil over here. Again, scope probes on the current. Now this is the current. Okay, let's get some measurements there. Now you're going to see there's big spikes there, and basically what's going on is we've got a bit of a fight going on in there. We've got a little bit of nice stuff. The nice stuff is that the current is moving in a positive direction on this upward peak. It's moving in a negative direction on this downward peak. The slope there, or the curve there, is good. We've got a good bit there, but we're far from a resonant sort of setup, aren't we? This is nice, but if we were to overlay them, put one on top of the other, then we do have, there's a lot of opposition there. We've got a lot of good stuff going on, but it's far from a nice, smooth, resonant system. Okay, we've got measurement bridge again. We've got capacitor 0.22 connected across the small coil. Okay, so that's directly connected across that. Okay, out to our load. We've got a bit of a voltage there. Input consumption, not too bad. Okay, but you can see here we've got a bit of a fight going on. We're not in resonance, we're not close to it or anything yet. There's still a little bit of work to be done. You can see there is a difference in currents, 557 compared to 534. Now obviously we want to maximize the difference. Okay, we've got to think to ourselves that the difference between the currents is what we are generating. That's the current that we're pumping, the difference between the currents. If the current is the same, and even if we have equal and opposite currents, if the current is the same in this configuration, then we are generating no current. Okay, so we're going to try and get a little bit better. We're going to work a little bit more on it, try and get the resonance a little bit better without it cutting out and everything. Remember, start off small. Start off with very, very low voltage. You can see mine's 2.7 volts. I've got 400 milliamperes going into it at the moment. And what I'm looking for is I'm looking for the optimum point where we've got as much current being generated as we can, but at the same time we've got as much voltage as we possibly can. Okay, And remembering again, the difference between the currents is the currents that we're generating. And the machine is pumping current. Okay, we're accelerating electrons through the wire.
The devices which I have invented, which there are a number of them, they all actually accelerate electrons.
Okay.
They're electron accelerators.
You've got to remember that we're forcing them through. It's an opposition of magnetic fields, and we're forcing the magnetic fields because the current that we're drawing, we're forcing the magnetic fields to be opposite. Okay, because we've got a non-inductive wire. So we need to get this whole thing just a little bit better. We've still got a little bit of work to do. We're going to find the optimum frequency and we'll be back. Alright, so we're doing another test. What we've done is we've taken the capacitor off where it was before, and what we're doing is putting the capacitor on the second leg. So now this time is on the capacitor is on the bigger coil. Okay, so the capacitor is no longer across the shorter coil, which is this one here and that one down there. It's on the longer coil, which goes the length of the former. Okay, and it's now resonant to the best of my ability, even though it doesn't look like it's resonant. It's the same capacitor as before, 0.22 microfarad, same setup, current probes, all that sort of thing, light output. Now this meter at the moment, even though I said the meters were pretty good before, this meter is not reading 100% correct at the moment. It's not far off. It might be maybe half a volt off. Okay, so reading our PSU. That's the scope. Now you can see there at the moment we are a little bit over twice. Okay, so our CRMS is sort of floating around about the 540. We are down on this channel, we're floating around about the sort of the 270 mark, roughly. So it's jumping up and down depending on what the spikes are coming through. This test is a bit of a failure. I'm not very happy with this test. This test is, it's not. I'm not happy with what's going on. There's too many spikes in the system. It's just an outright not very nice sort of setup. You can see the waveforms there are all over the show, spikes, all that sort of thing. There is a bit of a round in there on the peaks in here. If you zoom into it a little bit better, I've got it zoomed out so that we can try and get these values here stable. Otherwise the values tend to jump around a little bit. Anything off scope, off screen, tends to throw everything out, as most of you will know. So that's the setup. Again, not happy with it. I think very soon we're going to change it. We have a reasonable output, but the output's most certainly not ideal. Again, 2.7 volts, 0.4. Currently running at a 25% duty cycle. Frequency is currently 2.4 kilohertz at the moment. Same as before, we've got high side switching. So the positive goes on to the MOSFET here, negative out, and then back to negative again. So we've got high side switching. Haven't measured that yet. We might do that now. I'll pause the video and we'll throw that on there. We know what the output is. Alright guys, this is the input. We're on to a second test. Mean input current, we're looking at roughly 400 milliamperes, nearly 500. Let's say 470, 480 milliamperes. There's no, as you can see on the scope here, other than these little spikes that are coming through, there's no real big input coming through. CRMS is approximately the same as the mean voltage coming through, about 2.8 volts here, 2.8, 2.9 mean, which is pretty close to the PSU. PSU is reading a pretty good value there. Okay, output meter is it's a rough estimation. Meter is a little bit off. I've checked with the scope. This test we've got the capacitor across the big coil. Okay, so this is the underneath coil. This one here, it goes the length. So we've taken it off this short coil here, which it used to be on there and there. Put it on this coil, tuned for resonance. Currently sitting at 25% duty cycle, 2.4 kilohertz. Alright, so we've got a light bulb here. At the moment I've got a diode here, so half wave rectification on the output. You'll see in a minute. I'll take that off and show you the difference. Okay, so meter here, trying to get a little bit of a read. Digital multimeters, high frequency, very unreliable, so I don't recommend it. So please, what you see here on this meter, it may not be as accurate as what we think. Input again, we are just staying at the 2.7 volts. Scope again, so what we'll do is we'll switch it all on. Now that's half bridge rectification. They're the readings. So the top trace there, 165 odd milliamperes. Bottom trace, 203 odd milliamperes. So we're looking at a difference of roughly about 35 or so milliamperes. So not a lot at the moment. Again, measuring over here, probes on 1 times, in scope set to 10 times, both channels. Remembering that 10 times 0.1 ohms is 1 ohm, so that's the reason I do that. We're measuring across a 0.1 ohm resistor. It's a really easy way to do it, so if you can do it that way, it's so easy, it's just not funny. The scope just says, yep, no problem. So 10 times it, and it's basically 1 ohm. So the voltage that you read across that resistor, the voltage drop, is the voltage. All in all, this experiment is not as successful, not anywhere near as successful as the last one. Okay, so the big coil, the big secondary coil with more turns, 84 turns I think it is, when that is resonant with the capacitor, we don't get as good a result. The result's not as good. Again, we're looking at roughly 1.4 volts, give or take, and output 400 milliamperes according to that, and that's our light. Okay, all off. Go again with the, now we're getting a little bit more light. We are getting a little bit more voltage. We've gone up by 100 milliamperes, and that's our output there now. Okay, hopefully you can see that. So we're looking top trace 265 odd milliamperes, bottom trace we're looking at, it's jumping, it's around about the 300 mark, jumping round and about. So you can see our waves are equal and opposite. Okay, so back to that again. It means that we have whatever's coming up this wire is going all the way up to this short here. Okay, you can see that, so the short, and then it's coming back down again, back through the other wire, and vice versa. So when it comes up, it then comes back down. Remembering our coils, when our coils have equal up one way as what it does down the other way, we're pumping current, so we do get a current increase in some situations, not always, so sometimes it can be the same, and we've shown that already. So whatever's coming up will come back. Now turn for turn, if you look at this coil here compared to the coil that's wound underneath, so whatever's coming up this way comes back this way. Turn for turn, we're pumping current through that particular part of the coil. Okay. Now the big question, why do we need resonance? What's resonance? Okay, there's a big difference between magnetic resonance and LC resonance. Okay, when we have any sort of resonance, we get maximum amplitude. Okay, and that is the key. We need to get as much as we can out of these coils for as little input as we possibly can, so resonance is the way to go. Resonance between the coils, magnetic resonance, means that the magnetic field, the current, okay, is equal and opposite. It has to be equal and opposite all the time. Okay, and again, it needs to be at maximum amplitude. Now, you will be familiar that anytime there's a coil that has a current through it, or even a hose, various different experiments can prove this. But anytime you have equal and opposite, there is a reluctance, a resistance, okay, and we would have seen that before, and that's typical of bucking coils. Bucking coils has equal and opposite force. It doesn't want to let you do anything. The current bucks, the magnetic field bucks. We have a situation where there's, if you like, a magnetic resistance, okay, and that's the whole point of bucking coils, been the point of bucking coils in the past, and that's why people haven't gone any further. Now, the reason I'm saying this is what we need to do is we need to think about the currents in the coils. If the current in one coil is very much higher than the current in the other coil, we're going to find a situation where one coil will choke the other coil off, and we've talked about this before in the past. And remembering the idea of a choke, remembering that current will be limited depending on the magnetic field, okay, in the core. The whole idea of a choke is it's called a choke because it chokes the current off. Commonly used in the old days, not quite so much these days, although we still use it. So a choke would be to choke the current off, to stop the flow of current, and that's why we have a coil on a core, and you'll see it will be series in line with the circuit. Now what we're trying to, the reason I'm explaining that is because one of these coils will choke the other coil off. Okay, so what we've done is we've halved the turns between this coil here and this coil here, so current in this coil versus the current in this coil will choke the current off in one of these coils. And why is it going to do that? Is because one of the coils has a larger current than the other coil, which is what we want. We want to get the currents up. That's the whole idea of Mr. Prever experiment. Okay, but what we want to do is we want to do it in a fashion where it's not going to limit the other coil. Okay, and that's what we really are seeing in this experiment. We might have a little bit more output on the light. This bigger coil is in resonance, so this bigger coil has effectively a much bigger magnetic field than what this coil does, because turn for turn and current for current. Remembering yellow channel over here, okay, the yellow channel generally is carrying a little bit more current than what the red channel is, if you can see that. So we're looking at nearly 300 milliamperes compared to 250 on the top one. So the yellow channel is showing us that this coil, this top coil here, with turns from there up to the top here, does have a larger current in it. Okay, so up all the way through to the globe, and then all the way back again through this coil, all the way up and then back that way, and then back again. So it does have a larger current in it, and the magnetic fields are opposite. We can see that there. Okay, we've got opposite magnetic fields, equal and opposite. The little lumps that we've got there with the spikes in them, not probably the best waveform that we've ever seen, but at least it gives us something. Alright, I think enough talk. This video will be a little bit bits and piecey. It's been little bits of experiments all the way through, different days. It's taken a while to get to here. So maybe a review over the video a couple of times may help. Hopefully it's of use. Okay, video on. Last bit, just want to very quickly go through. We are low frequency, 2.7, 400 milliamperes, roughly 3.1 volts in the output. Decent output on the light, same as before, except no resonant capacitor here. Okay, so we're not using a resonant capacitor. Measuring the current on the output. Now we're getting a very capacitive looking fall here. On time is the 25% in here. Okay, so it's falling, it's going up, it's coming up, it's giving us quite a high amplitude, and then it's falling down. Okay, you could say this is the inductive spike. Okay, that's falling down like this. Now 25% here means we've got a 75% over here. So if 75% fall, okay, and the currents are equal and opposite. Okay, if we overlay very quickly, you can see there it's almost an exact match. We've got little peaks over here. We've got a little bit of what looks like capacitance on the on time. Okay, so we've got equal and opposite. We've got the trumpet waveform here. Currents roughly the same, 200, 200. Mean 7, mean about 10. Okay, so we're roughly the same. Now this is a very interesting effect. What we could sort of say here is we could say that the two coils are fighting on the 75% on off time. Okay, the two coils are fighting equal and opposite. This is current which is flowing through the coils, equal and opposite, after the 25% on time. So on time 2.7 volts, input coil 12 turns. Okay, and then when it's switched off we get the trumpet effect. Okay, very interesting effect. Now you can hear it's quite noisy. It's quite noisy for what it is. So again, half of the coil is non-inductive. We've got a fight going on, so one up, one back, fight going on in here, half reasonable output, and 3.1 volts. So this is something that's worth investigating further. Look at this effect, because this effect will prove to be valuable once it's understood properly. Remembering that coils have all sorts of values and all that sort of thing. The decay time is a factor in the coils. Remember what Floyd Sweet said about a signal passing through space. The signal passing through space does take time. Time is the critical factor. Alright, this video is long enough. Thank you for watching. If this video helped you, please consider a donation. We put a lot of effort into what we do. Our material is unique. You won't find material like this anywhere else. Thank you.